Hello everyone. Here we are going to work on a problem for planar or 2D kinetics of rigid bodies. We have a ladder leaning on the wall that has no friction. So there is no friction between the ladder and the wall and between ladder and the ground. As a result, due to the weight of the ladder, when you release it from this 30-degree angle with respect to the vertical direction, it is going to slide down on the wall and move to the right on the floor, and it is going to ultimately hit the ground. Now you release it from rest at angle 30 degrees. At this very moment, you want to find angular acceleration of the ladder, alpha, as well as the normal force applied by the floor on the ladder. So the first step, as always, is to draw the free body diagram, right? So you basically separate the ladder from the rest of the world, and see if I can do it a little bit better. So this is the ladder, and the forces acting on it are mg at the center, assuming that it's homogeneous. And you have a force here, N2, and you have a force here, N1. If there was friction, you had to add a friction upward here because this side goes down, and you had to add the friction to the left here because this side moves to the right. But there is no friction, so that's all you have for the FBD. The coordinate system, I'm going to use the traditional coordinate system, y upward, x to the right, and z out of the board toward us. And here I will also give a name to these points. I call the center point C, I call this point on the top point B, and the point on the floor point A. So at the moment, omega is 0. What we want is alpha, and what we want is force N1, the force by the floor. Okay, this is our FBD, coordinate system and everything. Now, how do we solve this problem? Well, as you know, the rigid body has 3 degrees of freedom in plane motion. Motion translation X, translation Y, and rotation Z. So we have 3 governing equations. Let's write them down. So we have sum of the forces along X direction, which in this case is N2. That is equal to mass of the block times acceleration at the center of mass in the X direction. Sum of the forces along Y is going to be N1 minus mg. Is going to be mass times acceleration at the centroid, the Y component. And sum of the moments about C, counterclockwise positive. Why counterclockwise positive? Because counterclockwise means positive z-axis. So if you look at that, the length is 4 meters, so each one of these distances from A to B or A to C is 2 meters. And this angle here is 30 degrees. So if we want the moments of mg does not have any moment about the center because it is passing through the center. N1 does, and N1, the moment it has about C is counterclockwise, so it's positive. N1 times the normal distance between point C and the extension of N1. So if you extend N1, like here, go up, this distance here is 2 times sine 30 because it's in front of the 30, right? This angle is 30 degrees. So it is going to be 2 times sine of 30 degrees. N2 has a clockwise moment, so it is going to be minus N2. And the distance for N2 is you have to extend the line of action of N2, draw a perpendicular from C to there. And this distance, as you can see, is cosine, right? So it is 2 times cosine of 30 degrees. This whole thing should be I about C times alpha. And you know I about C for a slender bar like this, if you can model it like a slender bar, as it says, with length L and mass M about the centroid, the formula from your statics was mL squared over 12, where m is 18 kilogram and L is the whole length of 4 meters. Okay, so now the question is, do we have enough equations to solve here for our unknowns? Well, if you take a look, you have 3 equations, so at most you can solve for 3 unknowns. But do we have 3 unknowns? Well, I don't know my alpha, I don't know my n1 and n2, and I also don't know my acceleration terms. And none of these acceleration terms, by the way, is 0, right? As this guy is going down, the center definitely moves, and that means the accelerations, since you are starting from 0 velocity, you need some non-zero accelerations to give you non-zero velocity. So when you go, for example, like this, now, if you look at your centroid is here. So clearly your centroid does move along both x and y. So none of these components is 0. How much are they? We don't know. But clearly you see I have 5 unknowns, right? So if I number my equation 1, 2, 3, I have 5 unknowns, and I cannot solve for the 2 unknowns of this problem. And so kinetics cannot give me any more equation at this point. And as I always say in my class, whenever kinetics is dead end, go back to kinematics. Go back, see what constraints you have, right? What constraints, what kinematic constraints can give you. So here you have point B to only move vertically on the wall and point A to only move horizontally on the ground. Those we have not used them so far, so we have to get some equation from them. How? So since here are the acceleration of point C, and that's what we need, there might be a chance that I can find them, or I can relate them to this alpha through my kinematics equations. How? I try to find acceleration of point C through point A and point B. So first, let's find it through point A. So I say A of C is equal to A of A plus alpha cross R of C with respect to A plus omega cross R of C with respect to A, correct? That's what we know for the relative acceleration between 2 arbitrary points on a rigid body. And as I said in my previous videos, if the problem is 2D, where omegas and r's are perpendicular to each other, r is in the plane, omega is out of the plane, you can simplify this double cross product as simply negative magnitude omega squared times r of C with respect to A, a scalar times a vector. That makes life a lot easier. Of course, in this case, you're starting from rest. At this point, your omega is 0. So anyways, this whole term is going to go to 0. Okay, so no worries. What is alpha? Well, alpha I don't know, but here I can assume it's in the positive k direction. It's either positive k or negative k. Let's assume it's positive k. And R of C with respect to A, clearly it connects A to C. So if this is my ladder, and this is C, and this is A, that's this vector, right? This is R of C with respect to A. It connects A to C. And clearly this vector has a length of 2, and the angle of that with respect to the horizontal axis is 60 degrees. So it is going to be 2 cosine 60 with a negative sign I, and 2 sine 60 with a positive sign J, correct? So if you want to write it as a vector, it is 2 times negative cosine 60 I and plus sine of 60 J. A of A is what? A of A, we know that the only constraint we have on A, it has to move horizontally. Okay, so it's either in I direction or negative I direction. What's the magnitude of it? We don't know. So here we just assume this is a magnitude that we don't know times I. A of C is what? Well, it has these 2 components, x double dot C and y double dot C. So if you want to write it, we write it as x double dot C times I plus y double dot C times J. And now you have 2 equalities, right? Two vectors are equal on the left and right, means the i's are equal and the j's are equal. On the left side for I, you have x double dot of c. On the right side, we have AA, and then we have k cross j, which is negative I, so you will get negative 2 alpha sine of 60 degrees. On the j component, we have y double dot c on the left. On the right side, we only have k cross I, which is j, but there is a negative component involved, so it's going to be negative 2 alpha cosine of 60 degrees. Now here I got two equations, but one of them, which gives me x double dot of c, the problem with this equation is it relates two of my existing unknowns, x double dot c and alpha together. The problem is it brings one extra unknown, a of a, which I don't know. So if I want to use this one as well, it gives me one equation but one unknown, which means basically it's not doing anything, because I'm only looking into equations that can help me solve this system of 5 unknowns and 3 equations. I want 2 extra equations without without bringing in a new unknown. So this one is definitely not something you want to consider, because it's not helping. It makes your 5 unknowns 3 equations, it makes it 4 equations, but makes it 6 unknowns. So it's not helping. But the bottom one does. The bottom one directly gives you y double dot of c in terms of alpha, so it doesn't introduce any new unknown, but it adds one more equation. So this is going to be my equation 4, and I do not use the top equation. So here I found one more equation, and I use the constraint that A has to move horizontally. So now it's time to use the constraint that B has to go vertically. And for that, I find A of c, this time through point B. So I say A of c is now A of B plus alpha cross R of c with respect to B minus omega squared R of c with respect to B. And this term is again 0 because omega is 0, and alpha is alpha k as we assumed last time. A of c is x double dot ci plus y double dot cj. R of c with respect to B, it goes from B to C like this. So it is very similar to R of c with respect to A, same direction, same line of action, same magnitude, opposite direction. So it's exactly like that, but just negate the component. So it is going to be 2 times positive cosine 60i and negative sine 60j. And finally, A of B, what is that? I don't know. It has a magnitude that I don't know, but it is definitely positive j or negative j. Now I know it's negative j. It's coming down from 0 speed, so you need a negative velocity. And negative velocity comes from a negative acceleration if your initial velocity is 0. So I know it is negative j, and I can assume it's negative j, but it's okay. I can just use the direction, use the line of action. Again, this gives you 2 equations, one for I, one for j. If you look at the i's, here you have x double dot of c, and on the right side you have k cross j, which is negative I. There is another negative, so you would get 2 alpha sine of 60 degrees. And then for j, I have y double dot of c on the left. On the right, I have a of b. And then I have k cross I, which is j, so I will get plus 2 alpha cosine of 60 degrees. And again, if you look at the bottom equation here, it introduces another unknown ab, which I don't know. So I'm not going to use this equation, and I only use the top equation, which relates 2 of the already existing unknowns together. So this one I call equation number 5. Okay, so now if you look, you have 5 equations and 5 unknowns. What you need to do is to replace 4 in 2 and 5 in 1 to get rid of the acceleration terms. So let's do that. I'm going to replace 4 in 2. If I do that, I will get N1 minus mg is equal to m times negative 2 alpha cosine of 60 degrees, and I plug in 5 in 1, and that will give me N2 is equal to m times 2 alpha sine of 60 degrees. And finally, I have my equation number 3, which if I write it for you, is going to be 2n1, correct? It was 2n1, and then sine 30 minus 2n2 cosine of 30. It was equal to m, which was 18, times L, which was 4, squared over 12 times alpha, right? And by the way, this m that you have also here, you can write it as 18, 18, and 18, right? So that was equation number 3. So now you have these final equations, and all you need to do if you want alpha is to eliminate n1 and n2. So if I call these now equation 6 and 7, 3 is still the same. We haven't changed anything, replace anything. So I can find from 6 and 7 n1 and n2 and plug it into 3, right? So if from 6 and 7 we plug them into 3, then I should be able to find alpha, because here you're going to get 2 for n1, you take mg to the other side. So this is going to be mg, and m is already 18. So this is going to be g, and then minus 2 alpha cosine 60. Cosine 60 is 1/2. So it's simply going to be 2 times alpha times 1/2, right? This is this one times sine of 30, and sine of 30 is also 1/2. And then minus 2 n2, and n2 is 2 times 18 times alpha. Sine 60 is the square root 3 over 2, so it's going to be 18 times the square root 3 times alpha. And then the result is equal to the here, if you divide by 6, that's 16, 8, 24 alpha, right? So this is the result, and it's clearly a linear equation in terms of alpha, and if you solve for alpha, you will get 1.84 radians per second square. And if you now plug it back into the equation that involves n1, which is equation 6, so if you plug it in 6, it can give you n, well, I need n1, yes, the one from the floor, and that is 6. So n1 is going to be 143.47 Newton. Okay, so these are my solutions: the angular acceleration at the moment and the force coming from the floor. And if you plug that alpha into 7, that gives you the force from the wall. Okay, so this is how you approach a 2D or planar kinetics problem of rigid bodies. You get all of the equations that you get from kinetics, and if you have more unknowns than these 3 equations, you need to get them from kinematics constraints, and you can get them through the acceleration motions, the relative accelerations, right? Which connects the acceleration of the centroid to another point where that point has a constraint. So by relating the acceleration of centroid to a point that has a physical constraint, you should be able to get some kinematics equations like these. Okay, and that's it. That's all you can get. Now, you can find these equations also in another way if you want. Okay, like if you write the constraint geometrically and then take time derivatives from that, you can also get this equation 5 and equation 4. And it's not hard here if you want to do it in this case, because what you have here is the centroid is here already. And if I ask you what is x and what is y of the centroid, right? So this is x of the centroid, this is y of the centroid. And this angle is 60 degrees. Then you would tell me that, of course, here y of the centroid is, y of the centroid is, that's 2. This is in front of 60, so this is going to be 2 times sine of 60. And x of the centroid is this whole length minus this portion. And this portion is 2 cosine 60, but the whole thing is, if you look, the whole length is 4, that angle is 30, so this length here is 4 times sine 30, right? So it's 4 times sine 30 minus 2 times cosine 60. So 4 times sine 30 minus 2 times cosine 60. Okay, so these are the coordinates of the centroid. Now, if in general you consider this to be angle theta, because we need to take time derivatives, if you consider it to be theta, then this angle here is definitely 90 degrees minus theta. And so if you want to write it that way, now here, sine of 60 is sine of 90 minus theta, which is clearly what? Cosine theta. So if you want, you can replace this whole thing with cosine of theta. And then, correct. Here, this is going to be sine theta. This is cosine of 90 minus theta, which is also sine theta. So it's going to be 4 sine theta minus 2 times sine theta. So it's going to be 2 times sine theta. So you can replace that whole thing as 2 times sine theta if you consider it with arbitrary angle theta. Now, if I take a time derivative from this, I will get x dot of c and y dot of c to be what? Well, here again we have to use the chain rule, so this is going to be negative 2 sine theta theta dot, and this is going to be 2 cosine theta theta dot. Okay, and we want acceleration, so I need to take another time derivative. Then you will get your y double dot of c to be what? Here, if you keep the negative 2 out, you have 2 variable terms, so it's going to be cosine theta times theta dot is the derivative of the first term. Then multiplied by theta dot, right? So it's derivative of first one times the second one plus first one times the derivative of the second one, which is theta double dot. And similarly, x double dot of c is going to be 2 times, and now here you have cosine and theta dot, so the derivative of cosine is going to be negative sine theta theta dot. You multiply it by theta dot, which is the second term, and then plus cosine theta times theta double dot. Okay, and if you want to replace theta double dot with alpha and theta dot with omega, here you will get negative 2 cosine theta times omega squared and negative 2 sine theta times alpha. And here you will get negative 2 sine theta times omega squared and positive 2 cosine theta times alpha. So these are x double dot and y double dot of c in general as a function of omega and alpha. At this moment, omega is 0, so if you take these two terms away, you see x double dot is 2 cosine theta times alpha, which I assume is this equation. We go down to those equations that we found. Right, let's see where we were here. X double dot is 2 alpha sine theta, but pay attention, this is sine of 60. Theta is the 30, so sine of 60 is cosine of 30, so this has to be like cosine of 30, which is my theta. So it is 2 alpha cosine theta, which you can see here. That's x double dot, and y double dot is negative 2 sine theta alpha, which again, if you go and look at this equation, that's the same thing, except as I said, cosine 60 is the same as sine 30 or sine alpha. Okay, so you can see you could get equations 4 and 5 through geometry and taking time derivatives. So either way that you took it, by using the relative formula or by taking these time derivatives, they are all good. I personally prefer the relative formula because the derivatives are already taken to give you this formula. Okay, therefore, you don't need to use geometry, you don't need to take time derivatives and make any mistake in the middle, right? Because if the problem geometry is more complicated, getting these equations is not always as trivial. And then if you do a smallest mistake in taking the derivatives, your final equation is going to be wrong. But these relative formulas, this single relative formula that is valid for every 2 points on the rigid body, is already taken care of so many of those considerations. So that is my preference for getting these constraint equations. But any ways that you do it, the solution should be the same. So hopefully the problem was useful to you, and I will see you in the next problem. Thank you.